Welcome, focused learners, to this explainer. Today, we're jumping right into a totally fascinating everyday mystery, and honestly, it's hiding right inside your refrigerator. We're going to take a look at a super simple, completely mundane object, the humble egg, and we're going to use it to unlock some genuinely profound rules of physics and dynamics. I promise you, by the end of this, you're never going to look at breakfast the same way again.
So let's set up our puzzle. Imagine I place two identical-looking eggs right in front of you. They've got the exact same shape, the exact same size, and they weigh exactly the same. But when we put them on a table and give them both a really good, strong twist to spin them, they behave in completely different ways. It's wild. One egg spins beautifully, smoothly and rapidly, just like a toy top. But the other egg, it wobbles unsteadily, kind of struggles to gain any real speed, and comes to this clunky, premature stop. So here's our starting point. Which one is cooked and which one is raw?
Section 1. The two-egg mystery. Okay, let's dive into this. The smooth, rapid spinner, that is the hard-boiled egg. And the wobbly, lazy spinner is the raw egg. But remember, their outward physical profiles, the weight, the shape, they're completely identical. So why does the heat of boiling fundamentally alter how this thing behaves when we try to spin it? I really want to challenge you to think about what is physically changing inside that shell to cause such a dramatic difference in motion.
Section 2. What is moment of inertia? This brings us to introducing our primary suspect in this mystery, which is a fundamental physics concept that governs all rotational behavior. To solve our mystery, we really need to understand this foundational concept. It's the rule that governs whether something wants to spin or whether it stubbornly wants to sit still. It's called the moment of inertia. Basically, moment of inertia is just an object's resistance to rotation. Think about regular linear motion for a second, right? If you try to push a giant, heavy boulder, its mass resists your push. Well, moment of inertia is the exact same concept, but for spinning. It's the resistance to rotational motion. But, and here is the absolute critical detail, it's not just about how much mass the object has. It's about exactly where that mass is located. The further the mass is distributed from the center axis of rotation, the larger the moment of inertia becomes, and the harder it is to get that object to start spinning.
Section 3. Internal battle. Liquid friction. Now, what's really interesting about this slide is how we can analyze what is physically happening right inside the shells of these two eggs. We have to look past those identical white shells and visualize the internal state of the matter to actually see how this physics concept applies. Over on the left, we've got the raw egg. Inside that shell, it is pure fluid chaos. It's a liquid. When you twist the shell, the solid shell starts moving immediately, sure, but the liquid inside is totally free to move independently. It actually drags and lags behind. Now on the right side, we have the boiled egg. The cooking process has locked all those proteins together into a solid unified mass. So when you spin the boiled egg, the shell and the inside move entirely as one single synchronized unit. There's zero energy wasted trying to drag a sloshing liquid along for the ride.
Let's look at the math that makes this all happen. This equation right here governs rotational motion. Torque equals moment of inertia multiplied by angular acceleration. Now, don't let the terms intimidate you. Torque is just the twisting force your hand applies to the egg. And angular acceleration is simply how fast the egg speeds up its spin. When you spin that raw egg, you're applying a certain amount of torque. But because the liquid inside is moving outwards and lagging behind, it creates a much larger effective moment of inertia. Because that value is higher, the angular acceleration literally has to be lower for the exact same amount of twisting force.
So the crucial point is that the moving liquid inside the raw egg is actively fighting you. As the shell spins and the liquid lags, they literally rub against each other. This creates internal friction, also known as viscosity. That sloshing liquid acts exactly like the brakes on your car. It steals the rotational energy you just put into the shell, completely wastes it, and forces the egg to come to that early, wobbly stop.
Section 4. The sudden stop test. So how about we propose an empirical test that literally anyone can do at home to absolutely prove this liquid friction theory? A great explainer doesn't just give you theories, right? It gives you proof. We can run a highly empirical, incredibly fun physics test right on our kitchen counter. First, take that raw egg and give it a good spin. Second, tap it with your finger just firmly enough to suddenly stop the shell. Third, lift your finger and release it immediately. And fourth, just watch what happens. The egg will mysteriously start spinning again all by itself. Why does it do that? Well, imagine this. While your fingers stopped the solid shell, the fluid liquid inside was still swirling around with all that momentum. Once you release the shell, that spinning liquid transferred its energy right back to the solid exterior, pushing the egg back into motion.
It almost looks like a ghost is spinning it, but no, it's just the laws of dynamics in action. Now contrast this directly with the hard-boiled egg. If you repeat the exact same sudden stop test with a cooked egg, it will stop completely, and it will stay dead still, because its interior and exterior are a unified solid mass. Stopping the outside shell stops everything at once, instantly. There's no rogue, sloshing liquid inside to carry any leftover momentum. It is a really perfect visual demonstration of a unified moment of inertia versus a chaotic one.
Section 5, From Eggs to Rockets. Let's move to and see how this builds into massive, high-stakes, real-world engineering.
What makes physics so absolutely incredible is that the exact same dynamics happening on your kitchen counter are governing these massive real-world applications. Look at these. The identical rotational principles that stabilized our boiled egg are used to design gyroscopes. These are absolutely crucial for keeping airplanes and rockets perfectly balanced in midair. Or think about the engine in a car. Engineers designed a specific component called a flywheel purely to have a massive moment of inertia. Just like our heavy, unified boiled egg, a high moment of inertia strongly resists changes in speed. That means it keeps the car's engine rotating incredibly smoothly instead of jerking around all over the place.
And this brilliantly illustrates our final concept, the conservation of angular momentum. This is exactly why you see an Olympic diver tuck their arms and legs in super tightly during a flip. By bringing their mass much closer to their center of rotation, they dramatically decrease their moment of inertia. And because angular momentum must be conserved, it's a fundamental rule, dropping their moment of inertia instantly skyrockets their spinning speed. They are manipulating the exact same physics rule as the sloshing liquid in our egg, just in reverse.
It really is kind of amazing how a super simple kitchen item can unlock everything from car engine design to rocket stability. I mean, we started with two identical-looking eggs, and we ended up unraveling the fundamental laws of rotational dynamics, internal friction, and angular momentum. So here's my final provocative question to you. Next time you are standing in your kitchen boiling an egg, are you ready to look past the mundane and watch a live dynamics lesson unfold right in front of you? Keep looking for the hidden science in your everyday life, and as always, keep learning.